In this section of the course, we are going to cover one very important topic in modern deep learning, which is called transfer learning. This lecture will introduce you to both the intuition and implementation of transfer learning, so by the end of this, you'll be able to understand the subsequent code. The nice thing about transfer learning is it allows you to obtain very good, often state-of-the-art results with less effort and less resources spent. The intuition behind transfer learning is this. Let's start with the basic observation that, in a CNN, the features that are learned at each layer are hierarchical. In the beginning layers, the CNN only learns some basic lines and strokes. In the later layers, the features get progressively more complex, from lines and strokes to parts of faces, eventually to full faces. This is, of course, if you trained your CNN on images of faces. You can also train your CNN on other types of images as well, of course. But here's another basic observation. We recognize that the initial layers learn to recognize just simple lines and strokes. Is it plausible that other tasks that don't involve looking at images of faces would still find line and stroke features useful? The answer is yes, because probably all pictures will have lines and strokes. The difference between a car and a face being that the way that you put together those lines and strokes will be different. In this way, we can imagine that the first few layers of a CNN might be useful for a wide variety of tasks, from facial recognition to vehicle classification to recognizing anomalies in medical images. This is the basic idea behind transfer learning. It's the idea that the features that I found for one task could be useful for some other task. Transfer learning really took off in the field of computer vision, so that's what we are going to focus on in this course. Probably the most widely known large-scale image dataset is called ImageNet. This is a dataset that contains millions of images and 1,000 categories, meaning it can recognize 1,000 different objects. Every year, there is a contest to see who can build the best image classifier on this dataset. The nice thing about the ImageNet dataset is because it's such a large dataset containing so many different kinds of images, we can transfer the features learned from this dataset to a wide variety of tasks. Suppose we wanted to build a dog versus cat classifier. That's easy because ImageNet already knows how to classify dogs and cats. Suppose we wanted to build a car versus truck classifier. That's also easy because ImageNet already knows how to classify cars and trucks. It's even possible for us to use the same features for things ImageNet has not seen before, like say images from a microscope. Alright, so that's just the high-level intuition. Let's go deeper and discuss how this will actually work conceptually. First, we recognize that it's not feasible for us to train CNNs on ImageNet ourselves. Although it's a lot less expensive and time-consuming these days compared to the earlier days of deep learning. In the old days, it was common for CNN training to take on the order of days, weeks, or even months. Nowadays, we have distributed training, multi-GPU clusters, and so forth. But at the same time, it's still not really something you want to do on your own. Luckily, many of the major CNNs that have won the ImageNet contest in the past have released their pre-trained CNNs to the public. So there's no need for you to do any hyperparameter tuning, try out different learning rates, and so forth. All that has been done for you, and the results are open source. Doubly awesome is that these pre-trained networks are already included in PyTorch. We'll discuss what they are and how to get them later. Let's say you found a super powerful, state-of-the-art CNN trained on the ImageNet dataset, and now you want to use it to do transfer learning for your specific task. How can you do that? Well, let's start with a picture. This is a picture of a typical CNN. It's a series of convolutions and poolings, followed by a series of dense layers. One perspective on the CNN is that it's made up of two parts. Part 1, which involves convolutions and pooling, make up a feature extractor or a feature transformer. It takes your raw image and converts it into a feature vector, which is a useful representation for ANNs and other machine learning models. Part 2 is just a feed-forward neural network, or an ANN, which we learned about earlier in this course. We can think of Part 1 as the body and Part 2 as the head. So here's how transfer learning works. What we do is we chop off the head, keep the body, which is a useful feature transformer, and then attach our own head. This head can be used for whatever task we want to perform, for example, identifying cars and trucks. In that case, we might use a logistic regression with a sigmoid output, since as you recall, the sigmoid activation is the appropriate activation function for binary classification. Optionally, you could add more layers to make it a feed-forward ANN. Here's another important detail about transfer learning. There are a few approaches to this, and I'm going to teach you about the most important and the most basic version. The idea is we're going to freeze the weights of the body and only train the head. In other words, only train the logistic regression layer. You can imagine that if we used a gigantic pre-trained CNN with 100 layers, it would train very slowly because we would have to update all the weights of a 100-layer CNN. But by freezing the body, we can simply ignore those weights and only train the weights of our own linear model. The important point is, we don't need to train the convolutional layers because they have already been trained on a dataset much larger than anything we could have gathered ourselves. The weights we already have for those convolutions are very good. There's no need to try to make them better. Instead, we can assume that they give us good features and worry about training the top. One major advantage of using transfer learning is that you don't need a lot of data to build a good model. You might recognize this graph, which basically says that the more data you have, the better your deep learning model is. This is opposed to classic machine learning methods, which tend to plateau after a certain point. So you might think, in order to build a good deep learning model, you must have a lot of data, which will in turn make your neural network take a long time to train. But with transfer learning, this work has been done for us. We don't need a lot of data because the earlier features were already trained on a lot of data. More data than we could have practically handled ourselves. And so transfer learning allows us to get the benefits of deep learning without needing to have a ton of data ourselves, and on top of that, it means we can train our model a lot faster. Not only are we just training a logistic regression, but we have a smaller dataset compared to what we would need if we trained our model from scratch.